This diagram shows the infamous 1-2-4 cycle of the Collatz conjecture. For decades, mathematicians have tried to prove that every positive integer eventually falls into this exact loop. But proving it for all numbers means ruling out the existence of ghost cycles, theoretical loops or divergent paths hiding infinitely far down the number line. To find these hidden cycles, we have to look across all places of rational numbers at once. This equation is the global Adelic constraint. It states that any true Collatz counterexample cannot simply diverge in standard integers. It must maintain perfect equilibrium across both Archimedean and non-Archimedean places, satisfying this exact product formula. This flowchart outlines a 6-step computational pipeline designed to hunt for that global equilibrium. We start by building truncated inverse trees at the top and work our way down to test for residual dissonance, a mathematical signal that a ghost cycle exists. Brute force arithmetic can only check one integer at a time, making it impossible to verify the infinite extent of the number line. To solve this, we move beyond simple calculation and use spectral projections to analyze the structural shape of the entire map. This diagram outlines the inverse Collatz rules paired with an adjacency matrix. If we work backward from any number m, we always identify an even branch by doubling it. And if m-1 is divisible by 3, we also map an odd branch. Those specific branching rules directly populate the binary matrix you see on the right. Every time a number connects to a predecessor, we place a 1 in the corresponding row and column. This creates a combinatorial transfer operator, which acts as a complete map of every reverse path we calculate. This is the Schur complement equation, displayed alongside a matrix partitioned into 4 quadrants: B, C, C transpose, and D. We use this formula to separate the known Collatz cycles, the main spectrum, from any potential anomalies hiding in the internal spectrum. By computing S equals B minus C times D inverse times C transpose, we mathematically eliminate the deepest layers of the graph. The internal spectrum is discarded entirely, leaving us with only the residual core. In this calculation, the term we subtract represents the contribution of the tree-like branches. By removing it, we collapse the outer layers of the graph to see what remains at the center. If a hidden anomaly is truly present, it will appear as a non-zero remainder that this elimination process cannot wash away. This table compares different ways to partition our matrix. Grouping the numbers purely by their depth in the graph, as shown in the top row, causes the process to fail. Many deep nodes have no lateral connections, which forces block D to become singular. When D is singular, the Schur complement formula breaks. To guarantee a cleanly separated, equitable quotient matrix, look at the bottom row. We partition the nodes by both their depth and their residue modulo 2 to the k. This simultaneous refinement keeps the intersection numbers constant and keeps the matrix invertible. Let's test this setup. Pause the video and practice writing out the B, C, C transpose, and D matrices for this simplified 4x4 adjacency matrix. Set up the exact quadrants for your own Schur complement. Here is the correct distribution for each quadrant. Once you have these blocks accurately defined, you can plug them into the Schur formula and execute the discrete projection. This graph plots the results of the next pipeline step. We extract the p-adic valuation of the residual core, labeled here as En, and fit it to the Iwasawa equation. En equals lambda times n plus mu times p to the n plus nu. Notice the 2 paths on the chart. If the data requires a positive mu value, the valuation curves upward along the dotted line, physically signifying anomalous growth, a ghost cycle. If we only find the standard 1-2-4 loop, the sequence forms the solid, flat line of zeros at the bottom. That algebraic fit provides a definitive, quantifiable test. We don't have to guess if a Collatz counterexample exists in our data. We just check if mu is greater than 0. When we process a network with more than 4,000 nodes, the elimination steps act as a massive filter. We are taking thousands of individual relations and compressing them down to that single small 3x3 block. That final residual core reduces exactly to the cubic factor, t cubed minus 1/4 equals 0. The 3 resulting eigenvalues are precisely the cube roots of 1/4. Across every test, the spectral radius stays exactly at 2 to the negative 2/3 power. It does not drift as we add more numbers. This shows that the system is mathematically rigid. The arithmetic complexity of the cycle is already fully formed at the smallest scales and never grows, no matter how many integers we add. To reach this conclusion, we built the inverse Collatz graph, isolated the residual core using Schur complements, and tested the valuations for anomalous growth using the Iwasawa fit. While this specific pipeline did not produce a counterexample, it verifies our methodology. We proved that we can take infinite topological noise and filter it down strictly to the inescapable 1, 2, 4 cycle.